this is where we were. Any questions before I start the second part of this module? All right, let's start with a different type of instructions that we covered. Control flow instructions and arithmetic instructions. These are the logical operations. In CPU, we have an important block called ALU. ALU is arithmetic and logic unit. So arithmetic operations are add, subtraction, and so on. And we have logical operations like this. We have AND instruction. C, we just use AND. In MIPS is AND on AND immediate. When we're actually working with a number, use AND immediate. We have bitwise OR. MIPS instruction for bitwise OR is OR and OR immediate. We have bitwise NOT. We use NOR for that. And shifts, different types of shifts. We have shift left and shift right. And shift left and shift right, as you can understand from its name, it shifts bits to left or right. And it's an R-type instruction, because the only format that has space as a field for shift is R-type. Alright, this is a very useful, these types of instructions are useful when you want to extract some bits from registers. We had some examples of that, and we talked about it briefly last session, that you can use AND instructions or instruction to extract specific bits from a register, because we don't have byte level access to the registers or bit level access to the registers. All of the instructions in MIPS work with registers. The lowest granularity that you can have is moving one register to another register. But if you want to work with bits inside the register or bytes inside the registers, that's where you need to use these types of logical operations, and you can use AND and OR to mask them. Okay, so let's have some example here. We have a MIPS instruction that wants to return the lowest 4 bits of register T2 to register T0. We have a value in register T2. We just want to get the lowest 4 bits of that and move that to T0, and everything else is going to be 0. So what type of logical operation do you think we can use here? Before going to the details of how we should do, what numbers we should use, but how can we mask a number, a value, and just keep some part of that and the other part 0? AND instruction, right? Because when you AND something with 1, and x with 1, it's going to be x itself, and AND with 0 is equal to 0. These are logic design, basics of logic design. So if you want to keep the last 4 bits of T2, we can use a temporary register and store value in that temporary register, and then AND these 2 registers to keep those specific bits. So let's see how it works. I moved the number 15 to register T1, which is a temporary register that you can see here, and then AND T1 with T2 and move the results to T0. So let's see how it works. Let's assume that we have some number in T2, okay? So this is just something in T2. And then we have T1 as 15. So when you have the binary representation of 15, everything is 0 here, and the first 4 bits, the least significant 4 bits are 1. So now if I AND T1 and T2, because I'm using the bitwise AND here, it's going to keep the value in T2 for the least significant 4 bits, and everything else will be 0. And this is what we're going to get. Everything else is 0. The lowest 4 bits, the least significant 4 bits, are the least significant 4 bits of T2 as well. Does that make sense? Okay, so now let's have another example. This time we have a MIPS instruction that wants to return in T0 the lowest 4 bits of T2 unchanged when all the other bits are set to 1. So it's pretty much like the opposite case of what we just had. It wants to keep the lowest 4 bits and everything else becomes 1. So what type of instruction should I use here? OR. And what should be the number that I store in that temporary register? obviously it's going to be hard to say in decimal. Let's just explain it, it's fine. You know what, Rashina? So everything is 1, and then we have 4 zeros on the right side. When we OR that with 0, it's going to return itself. When we OR something with 1, the output is going to be always 1. So this is what you're going to get. But the number it's easier to show it in hexadecimal. We're going to have 7F, and then 1 0. And it's actually something like this. So T2, let's assume T2 is this. And T1 is going to look like this in binary. Everything is 1. And then we have 4 zeros here. When you OR them, or when you OR something with 1, you're going to get 1, or something with 0, you're going to keep getting self. So this is what's going to happen. So with the same method that we use here, we can extract any bits. Right? If I had 0 here and F at the end, I extract the next 4 bits. I can extract the bytes and everything. And then I can shift them right and left if I want to do it. Okay, this is how we extract numbers, extract bits. Shift left and shift right are also logical operations, but they have more important usage too. So let's see if we can, before getting to shift, because it's instruction encoding, let's talk about encoding these types of instructions. So some example of instructions are AND, OR, NOR, as you can see here. These are all R format instructions because there are 3 registers involved in this instruction. Very simple. 3 registers, R format. R format has, just a reminder, has 6 different fields. We have opcode, source register, the second source register, destination register, shift amount, and function field. We mentioned for R format instructions, opcode is always 0, and function field is what is the field that identifies the instruction itself. So if you go to the reference sheet, so I think I have it here. Yeah, so this is an AND instruction. If I look at AND here, I see the opcode is equal to 0, and the function is a hexadecimal 240x24. Okay, so you need to know how to use this reference sheet, otherwise you're going to have trouble in the exam. So AND instruction, I find the function field. Then I have register T1 and T2. Register T1 is going to be the first source, so T1 is going to go here. Again, as a reminder, T0 is 8, so T1, the index number for T1 is going to be 9. The index number for T2 is 10. So in the first source, we move 9. In the second source field, we move 10, the decimal value of 10. And because it's not a shift, this one is going to be 0. Opcode is 0, and the function field is 0x24. As a reminder, you need to pay attention to how many bits I have for each field. We are not going all the way to hexadecimal right now, but 9 is, for example, 1001. It's a 4-bit number. But because the field has 5 bits, what we put in the field is going to be 0, 1, 0, 0, 1. The same story with the hexadecimal number here. When we have 0x24, 2 is going to be a 4-bit number, and 4 is going to be a 4-bit number when it convert it to binary. But you do the conversion, and you get rid of the most significant 2 bits, because we only have 6 bits in the function field. Okay? I just write it here one more time. 0x24 is going to be 0, 0, 1, 0, is 0, 1, 0, 0. Because we have 6 bits in the function field, we ignore these 2 bits. If I ask you to do the conversion, this is what you should do. Alright, so this was for an AND instruction. We also have immediate instructions for AND, for logical operations. For example, AND I and OR I. And as we showed in the example, we can AND something with a hexadecimal or a decimal number. So this is how it looks like. And if you want to do the encoding for that, OR immediate is an immediate instruction, is an I-type instruction. So this is how I-type instructions are formed. We have opcode field, we have RS and RT. RT also plays the role of the destination register in the immediate type, in the I type. to mention that RT should be the second source. There's a destination register here. So that is then this is T0. Destination register is T0 with 8 here. The source is T1. The opcode for OR immediate, you can come here and check the OR immediate opcode. Opcode is 0x0D. And the constant value is going to be here. We have a 16-bit constant field. All right. Any questions? All right, shift operations. We have 3 important types of shift operations to talk about here. There are more types, but you can check the book, or the Morse has a help part that you can see all the instructions. The 3 shift instructions that we're going to talk about today is shift left logical. Shift left logical shifts all the bits to left, and you have to define how many shifts you want to have. But it shifts everything to left and replace the number on the rightmost with 0. Shift right, move things to right, and replace the numbers on the left side with 0. And then we have shift right arithmetic that shifts everything right, but it keeps the sign bit. Right, the negative number is going to remain negative. And the way it does it is through keeping whatever we have in the most significant bit. The most significant bit is representing a sign. We keep the sign, we shift everything to right. Okay. Example of the shift left logical. So this is a little bit different, and it can be confusing because it looks like an I-type instruction, but it's not an I-type instruction. It's a shift instruction. We have number 8 here, for example. In the first view, you think, okay, I have a number, and it's an I-type instruction. It's not, because we're dealing with the shift, and the only format that has a field for shift is R format. So this is what we have here. But then it gets a little bit more confusing because we don't use the first source register field in shift, in cases of shift. So we have a number. This number is going to go to the shift amount field. Then we can find the opcode and the function field from the reference sheet too. But S0 is going to be in the second source field. So S0 is going to go to RT, and T0 is going to be in RD. So destination register is where the destination register is supposed to be. But this, the common sense is using the first source. I don't know why they didn't use that, but they're using RT for that. Okay, so RS is not used. If I ask you to do the conversion, you have to remember that shift is a little bit different. So you can go back and check the slide and make sure they are doing the conversion the right way. Any questions? Good. Okay, so now let's talk about the control instructions, the MIPS control flow instructions. These are some reminders that are important because you want to know how we calculate the target address in these instructions. So to remind you, we have branches and jumps that were control flow instructions. I mentioned, I think 2 weeks ago, that when we are running this MIPS assembly instruction, MIPS assembly code, and it starts from the first instruction, it goes to the next one, and the next one, and the next one. So if you want to create a loop, you are the one who is responsible for moving the instructions around, jumping to different labels. Okay, but how do you really do it in hardware? How do you really do it in a computer processor? The only thing that you have access to is program counter. So we have the MIPS code. The MIPS code is stored in instruction memory. And then through this control flow instructions, you change the value in the program counter, and you move this to different places in the instruction memory. Okay, so this whole idea of working with program counter to go to different places in the instruction memory is what we need to know and have in mind when we want to do the encoding for this type of control flow instructions, both for jump and branches. You have to keep in mind that I'm adding something to program counter. I'm working with the instruction memory. Okay, instruction memory is a byte accessible memory. Every instruction is a word. So these are the things that we talked about, but these are the things that you have to keep in mind when you want to do the encoding as well. Okay, so now with that information, we have two basic branch instructions. Obviously, we have more pseudo instructions, but here we just talk about the basic instructions because we want to do the encoding, and actually only the basic instructions can be encoded. Pseudo instructions should be converted to basic instructions first, and then they will be encoded to machine code. So we have branch not equal and branch equal. It's an I format instruction. The opcode for branch not equal is, for example, 0x05. And if you want to see the opcode for BEQ, the opcode for BEQ is 0x04. We don't have a function field in I format, and that's why we don't have anything here. Not applicable. Now we have RS and RT here. So RS is the first source, and the first source is this register, and RT is this one, and we use S1. In this case, does it really matter which one is the first source and the second source? It doesn't really matter because you're just comparing two registers, right? So if I ask this question in the exam, and if you place these two and put RT here and RS there, it's still fine. Because it doesn't really matter, we're just checking if these two registers are equal or not. Okay? So, but the first source is this one, the one on the left side, and the second source is this one, S1 in this case. And then we have the offset value, label. If you have a label, we have to find a way to find the offset, which I'm going to explain. In some cases, you can actually have a number. Okay, so this can be branch equal S0, S1, and 4, for example. It doesn't always have to be a label. We're going to see some examples. So now, how do we calculate the address? Okay, we have this offset value. Based on this offset value, we need to calculate a target address, or target branch address, or branch target address. So what we do is, we multiply offset by 4, and add that with the address of next instruction. So there are two things that you need to remember from our previous discussions. So can any of you tell me why do let's start with the first one. Why do I multiply offset by 4 here? The word is 4 by, that's right. But what does it have anything to do with this one?
It's also like the number of steps you are going from the first address, so it should be multiplied by.
That's right. So the answer is, the offset is going to tell you how many instructions you should move forward or backward from where you are to take the branch. Okay, if I have, for example, BEQ, S0, S1, and loop, then I go and check the label for loop and see how many instructions I should move forward or backward to go to the loop. So the offset is not telling me the address, it's telling me how many instructions I should move forward. Okay, so, but when we're accessing different bytes in the memory, instruction memory is a byte address of a memory, every instruction is a word. So when I say move 4 instructions, move forward 4 instructions, if I want to convert that to the address, I have to multiply 4 by 4 because each instruction is a word, and that's why we have multiplication by 4. But can you tell me why do I add it with the address of next instruction and not itself? This is, we already have the answer up there. This is something that you might not remember from the intro. So we have 5 steps in MIPS. We have fetch, decode, and so on. So when we fetch an instruction, when we go to an instruction memory and get the machine code, right there we do PC plus 4. So 2 things happen at the same time. Reading the instruction from the instruction memory and adding PC to point to the next instruction. So when you are in the decoding phase, your PC is already PC plus 4. You are already pointing to the next instruction. Okay? So when you have this offset, If you want to find the target address, you have to get the offset multiplied by 4, but added with the PC plus 4 because program counter is already incremented. When you're executing this instruction, program counter is already pointing to the next instruction. Okay? So I have 16 bits. As I said, you can move forward and backward with the loops, and you already know about it. When we move forward, we have positive values. When we move backward, we have negative values in the offset. So this is a sine number. When we have 16 bits, we can cover numbers from -2 to the 15 to +2 to the 15 minus 1. So these are the ranges that we can have. What it means is that if you have a pretty long code, okay, you have more than 2 to the 15 minus 1 lines of code, you're gonna have trouble branching to anything after that point. So you can't branch to the 15 plus 1 instruction after where you are. Okay, so how do we fix this problem? Let's say we have a pretty long, and that can easily happen. Don't think that's not gonna happen. Because when you have a C code, if you want to okay, so I'll give you an example. You have a C program, and it has loops in it. Okay, machine learning, for example. We have different loops in it. Compiler wants to convert that to MIPS. So right there, we have already seen that one C instruction can be 5, 10 MIPS instruction. Then we activate one of these optimizations that can happen at the compiler level. Remember the optimizations that we can do, which I forgot that it can actually happen in the compiler when I was explaining it. And let's say you activated one of those that is supposed to do loop unrolling. You're gonna go extreme with the loop unrolling, and then you can easily get thousands, millions of instructions if you unroll those very large matrix multiplications. So that can actually happen. It's not that it never happens. It is rare, you can never see it in your class because we're not going to have such a large project, but it can happen. So how can we jump to another place that is beyond this range? You probably don't know the answer for that now, but we're going to learn about it later. That's why we use unconditional jump. Okay, so when I discuss the encoding for non-conditional jump, you can see that the offset bits, the J-type instructions, one of the reasons that the J-type instructions are designed is because of this pretty large jumps that we want to make. The offset field becomes 26 bits, and right there you cover pretty much any types of code. Okay? So if I give you an instruction like this, if I give you the machine code and I ask you to calculate the target address, what you need to do is you can get the 16 bits, you shift it left twice. So what happens here? What is it doing? When I shift the number left once, what am I really doing? Multiplying by 2. So when you shift something left 1 bit, you're multiplying it by 2. When you shift it right 1 bit, you're dividing it by 2. Okay? So if you shift it left twice, you're multiplying that by 4. So right there, you're multiplying offset by 4. So you shift it left twice, do the multiplication, and then do the sign extension to get a 32-bit number. Okay? So you have this calculated PC, this offset multiplied by 4 here. Then you have PC plus 4. So this is exactly the hardware that we have in the fetch phase. So later when I show you the CPU architecture, you can see that we have a PC and an adder literally placed in the fetch stage. Okay, so PC plus 4 is happening here. Then I do that addition anyway, so I have a PC plus 4 and a PC plus 4 plus offset multiplied by 4. And I give both of these results to a multiplexer. What multiplexer does is that based on the control signal, it chooses one path or another. Okay, so the output can either be PC plus 4, directly coming from here, or PC plus 4 plus offset multiplied by 4. So your output is going to be either the branch address branch target address or the next instruction. Why do we have such a thing? Because in some cases we actually check the condition and we take the branch, but sometimes we check the condition and if the condition is not met, we simply go to the next line. This is how we work with PC. If the branch is taken, you go to PC plus 4 plus offset multiplied by 4. If the branch is not taken, you simply go to PC plus 4, which is the next instruction. Okay, so you place a hardware like this in your CPU to move your program counter around in the instruction memory. Okay, so where is the signal coming from? We're going to talk about it later. Somewhere in ALU we do the comparison. So we compare them, the output of the ALU is going to come and select the next address in the instruction memory. All right, so we have a MIPS instruction. It's BEQ S0 S1 label. We already provided the machine code to you, and we assume that the PC right now is 20. Can you tell me what the branch address is based on what we just discussed? Think about it and give me the answer. Machine code is here. Just a hint, don't worry about this, we don't care about them. We do care about the constant value. Raise your hand if you think you know the answer. If you're already looking at the slides, don't give me the answer. Go ahead.
52.
Is it Ian? What's your name?
Oh, Andrew.
Andrew, sorry. Okay, go ahead.
52.
52. Okay, so can you walk us through it? So what's the first step?
So I take the constant, which is 7, and multiply that by 4, so it's 28, and then add 4 to the
Okay,
program.
let's wait here. So we get the constant, that's right. We get the constant, we multiply that by 4. The constant is 7, when we multiply that by 4, we get 28. So go ahead.
I add 4 to the program counter for 24, and add those two together.
So why is so we have PC as 20, but we added with 4, we get 24. So PC plus 4 is 24, plus 28, we get 52. That's exactly right. Okay, so now let's do step by step. You get the constant value, shift it left twice, which is equal to multiplying it by 4, and this is what you get. This number is 28. Then you have PC plus 4 calculated. I mean, obviously, if you sign extended, you're still gonna get 28. It doesn't matter really. Then you have PC plus 4, which gives you 24. 24 plus 28 is equal to 52. That's the target address. Thank you, Andrew. And this is the binary representation for that. Does that make sense? Good. All right, so jump instructions, J-type instructions. So we covered pretty much a lot of R-type instructions, then I-type instructions, and now we have J-type instructions. So J format is pretty straightforward. It has opcode and 26 bits for the address. It's an unconditional jump. It's a pretty large number. It can cover from -2 to the 25 to +2 to 25 minus 1. That's a pretty large number. I highly doubt that anyone can have a code that's that big. Okay? And if you do, then you don't really want to run it on MIPS processor. Just use another processor for that. Okay? Okay, so how do we calculate the target address here? We get this 26 bit, and we we have the same story here. We kind of multiplied by 4 or shifted left twice. Then it's 26 bit is now 28 bits. But you also do something that is called concatenation. You concatenate the most significant 4 bits of the program counter and add it there too. So you have 26 bits coming from here. I want to find the address. So what is going to be stored in PC is this. Get the 26-bit address, shift it left twice, and concatenate the most significant 4 bits with the most significant 4 bits of the PC. Okay? But this is how you find the jump target address. Okay, now let's have this question. We have the program counter, as you can see here, and the J instruction is J label. So we want to write a machine code for this instruction if label is this. So what it means is that we have the target address, and we want to go from target address to offset. And if you find the offset, if you find the constant value in the J-type instruction, and you find the opcode, then we are good. So we're going to get the machine code from the target address. If you think that you can do it step by step, you don't have to give me the final answer, just raise your hand and we move forward and we'll see what's going to happen step by step. It's pretty much the opposite case of what I explained in the previous slide. In the previous slide we had the offset. We're shifting it left twice and we're concatenating it the 4 bits of the PC. Now we have to do the opposite thing. So what it means is, maybe I can explain. So this is J format instruction. It has an opcode field and it has an address field, 26-bit address field. So we have 32 bits here, it's the target address. We want to go down to 26 bits. We already know that this number is shifted left twice and something is added to the most significant 4 bits of it. So it's very simple. If I get rid of these 2 bits here and the 4 bits at the end, these are the things I added to the offset. I shifted left twice and added concatenated with the 4 bits from PC. So I get rid of the 4 bits most significant bits and the 2 least significant bits, and right there I have the offset. Okay? So let's see how it happens. First we get rid of this, and then we get rid of the last 4 bits, and this is what you're gonna get. So this is gonna be the 26 bits, and then you add opcode here. Opcode, you can find it from the reference sheet again. So this is the opcode for jump. Does that make sense? It's a pretty straightforward thing to do. You'll find the target address, you get rid of the most significant 4 bits and the least significant 2 bits, and you have 26 bits, you just put in an instruction in the field, constant field in the jump, J-type instruction. Alright, so we covered pretty much all different types of instructions, especially those that you're going to need to know when we go to designing the computer architecture, the MIPS architecture. Now let's have potential question in the exam. So I give you a loop, for example, like this, and now I ask you to encode every instruction in this loop. So here we have 1, 2, 3, 4, 5, 6 instructions. You have to encode 6 instructions and probably gonna have 30 points or something. You're gonna get 5 points for each instruction that you encode. We're gonna quickly, I'm not gonna do it one by one. There are 2 things that branches and jump that I really care about, but as a reminder, we're gonna quickly do it together. So we have shift left logical SLL here. What is the format for this instruction? What is it? It's an R-type instruction. So R-type instructions, we have opcode, RS, RT, RD, shift amount function. This was the case that we said it's a little bit strange because we don't really use the RS. So So RS is 0. It's an R format, opcode is 0. Destination is, the first source is S3, which is the index number for that is 19. The destination is T1, so we have RD equal 9. And the shift amount is 2, so we actually put 2 here. And the function field for shift left logical is 0. If you go and check the reference sheet, you're going to see that. Okay, so the next instruction is pretty straightforward. It's R format. We have 3 registers, and I'm not going to cover that because we talked about it enough. We have load word. What is the instruction type for load word? It's an I format instruction. So we have opcode, RS, RT, and then we have offset. Okay, so the offset value is 0, so we put 0 here. The source is 8, T1, the index number for T1 is 8, so we put 8 here. The destination is just here is the second source, is 9, and I put this here. And the opcode for load word is 35. So we are dealing with decimal values here, by the way. Now we have branch not equal, so this is the one that I want you guys to help. Branch not equal, what is the instruction type? It's not J. No. It's I format. Okay? So branch not equal is also I format. We have, this is one of those cases that say it doesn't really matter which one sits in RS and RT, but we just want to see if they are equal or not. So you can put either T0 in RS or S0 in RS, it doesn't matter. But what should be in the offset field? Just think about it for a second. So what was offset? To find the target address, we had PC plus 4 plus the offset multiplied by 4. Okay, so exit is here. And there's some instruction in exit. We don't know what it is, but there's something there. This should be, you can answer this question, go ahead.
Would it just be 2?
Yeah, why?
So, because you have to skip 2 instructions.
Yeah,
You do the PC plus 4, then you'd be at the next one after the branch is that one, and you skip 2.
So
yeah.
from here is skip 2, or from here is skip 2?
Well, you skip 2 from there, but
And there is BNE or add I, that's what I want to know.
Hmm?
So you skip 2 from here, 1, 2.
Well, skip meaning you just ignore those. You ignore 2 after the branch, but
Yeah.
like
Your answer is right, but you know that's not the reason we have.
yeah, that's not what it's.
So the reason is when we are executing BNE, we are already pointing to the next instruction. So when we're executing this one, we are already here. So from there, we have to go 2 instructions forward. So it's going to be jump and whatever is in exit. Okay. So can you tell me, that's the next question, what would be the number if I wanted to jump back to loop?
Back to where?
To loop. If it was BNE T0S5 loop. I explained exit one more time, and I expect you guys to answer loop one more time. So, what I did was, I want to jump to exit. When I'm executing this instruction, the PC is already here. So because I want to go to exit, I have to move forward 2 instructions, 1 and 2. That's how I found 2. I'm already in the next instruction, and move 2 instructions from there. So now what would be an answer if I want to go to loop?
-4.
Once.
-4.
So we go here, and we go 1, 2, 3, 4. That's the correct answer. So we're already in the next instruction, and we count how many instructions we want to move backward. If you want to put -4 here, don't forget about the 2's complement. You have to have 4, and you have to put a -4, and you have to do sign extension. That's where you're going to need 2's complement and sign extension. So So it's a relative addressing, as you can see here. Now, add immediate is a pretty straightforward instruction. It's an immediate instruction, so I'm not going to explain here. Now let's talk about jump a little bit. Jump loop. So jump is a J format instruction. It's clear. It has an opcode field and it has an offset field. Okay. So how do I find? And I want to jump to loop, right? How do I find the decimal value that I want to put in the constant field in the J format instruction? You have something like this in the previous example. You have the target address and you calculated the offset for that. Okay, so it's pretty much the same thing. Here you have the target address, which is 80,000 in decimal. Okay, so now what we would do was we would get rid of the 4 most significant bits and the 2 least significant bits, and then find the offset field, right? So if I want to do it the difficult way, I convert 80,000 to a binary representation, and I get rid of the most significant 4 bits, least significant 4 bits, and then I go from binary to decimal again. But is there a better way of doing it? Any ideas? Yeah. Forward way one more time. 80,000, you go to binary, get rid of the 4 most significant bits, 2 less significant bits, and right there you have a binary number, then you go to decimal. But is there any easier way for doing it? It is. So 80,000 is not such a large number. So why do I care? Because it means that most probably the most significant 4 bits is going to be 0 anyways. Because those are for 2 to the 31. We're not talking about billions here. Okay? So the most significant 4 bit is 0 anyways. And if I want to get rid of the least significant 2 bits, it's as if I'm dividing this number by 4. Right? So if I have 80,000, now what is going to be the answer in decimal? Then it's going to be 20,000. Okay? Because the most significant 4 bits are already 0 if I convert this 80,000 to binary. And then shifting it right twice is like getting rid of that those 2 bits is equal to dividing it by 4. So that's 20,000. It's an absolute addressing. This is how it works. Okay. The very last question here, and then we're going to have a Kahoot. So that's 3 questions. I think we're going to have enough time for that. So the following MIPS machine code instruction is in hexadecimal. So we have this in hexadecimal. And we want to find the MIPS assembly instruction for this one. Okay. So the first thing we need to do is converting it to binary. Okay, this is the conversion to binary. Decoding, we're working on decoding. What is the next thing we should do? We had another example like this. Do you remember what was the next step?
We have to check the opcode.
Right, so we have to check the opcode because all different types of instructions have opcode. So opcode is the most significant 6 bits. If I go to here, I'm going to see 000100. Now, I want to do this. So, now this is going to be the tricky part, which is not so tricky really. So this is 000100. I have everything in hexadecimal now, so that means that I have to first convert that to hexadecimal. So you have 000100. If I want to convert to this hexadecimal, this is 6-bit. I have to add 2 zeros to make it 8 bits. Then this is going to be 0 and 4. So this is the hexadecimal value for that number. Okay. Then we have 0804, which means it's the branch equal. Okay, from the reference sheet. So when you find the branch equal, you're good because you already know what the format of the instruction is. Branch equal is an I format instruction. So from there you can find the other fields that we have. Okay. So let's see this. This is a branch equal. It's an I format instruction. Now I populate other fields based on this binary number. First 6 bits here, the next 5 bits here, the next one here, and the offset. Okay, so now if I want to convert it, I know it's a BEQ, and I have to go and check these, the indexes for the registers. So this is 10, this is T2, this is 9, this is T1. Reference sheet, just check out if you can find it. So BEQ, T1, T2, and this is the, it should be 32. It's a typo, I fixed it. But, and this is where you want to jump. Wait a minute, no. No. What's the number here? Yeah, so this is 32. I'll fix it later. But then you just convert the decimal binary to decimal and you're good. Okay, I added it right before class and there's a typo, so I'll fix it. All right, so the last thing, we covered the MIPS instructions, different types of instructions that we have for MIPS. In the beginning of the class, I said if you know MIPS, you know you have a good amount of information about ARM2. So we're not going to cover ARM processes here, but let's see some types of instruction encoding instruction format that we have for ARM. So ARM is a little bit more flexible. They have more types of instructions, and all the instruction fields are not just 32 bits. So I think we have an example here that we can see. We get to have instructions that have less than 32 bits. So they use the instruction memory in a more efficient way, right? So they can have 2 instructions in 32 bits, for example. So they have a more efficient way of using the instruction memory, so they can store more instructions in the same amount of memory that we have. But the important thing is here that, okay, so now you know how encoding works. If I give you the datasheet of ARM, and if I give you the instructions of the architecture of the ARM, by having that information, you can also encode ARM instructions. It's the same exact process, right? It's just, let's identify the fields. Let's see what type of instruction it is. Let's see what registers we are working with. It's a little bit more flexible, it has more options, but it's pretty much the same thing.